And now, last but not least, we need to discuss optical connectors, the topic that was already mentioned a couple of times here. And we have Rolando Ferin among us, the Chief Product Officer of FEMTOPRINT, who will present the glass microcomponents for optical connectivity. Welcome, Rolando.
Thank you very much, Ivan, for the introduction and for the opportunity to spend the last 10 minutes of the day talking about glass microcomponents for optical connectivity. So first of all, a couple of words about FEMTOPRINT. FEMTOPRINT is a Swiss contract development manufacturing organization which is specialized in laser micromanufacturing and production of glass microcomponents for several markets. We are based, as I said, in Switzerland, in the south part of Switzerland. We have operation also in the west part of Switzerland, from where I'm talking, and also we have an office in California, in Ventura, which is relevant for what we are talking today, as you can understand. So the topic is how to make the fiber-to-chip connectivity and where are the bottlenecks and how we can solve them. We know that, let's say, in the AI deployment or in the deployment of data centers for AI, there is one big bottleneck which is linked to the development of this new optical transceiver we have talked about today. There are several approaches, pluggable optics, co-packaged optics, so all of them, they share one important point. We need to bring the fibers to the chip, and we need to connect the fiber very efficiently and in a scalable way to the chip. And it's what we do actually at FEMTOPRINT. We produce the optical components, microcomponents can be used to go from devices like integrated photonics devices, quantum devices, photonics devices for photon computing, to real systems and real system connected to fibers. To do that, we produce three types of products that can also be combined together, as I will show you at the end of the talk. First of all, micromechanical aligners for fiber alignment. You know that for these chips, we need to align the fibers very precisely in order to limit losses. Waveguides, glass waveguides for beam routing, and micro-optics means micromirrors or microlenses for beam shaping. And I will go through these three type of products one by one. I will start from the first one, what we call fiber Ferrules. This can be usually, the standard product is a V-groove array, one V-groove array, but today we get more and more requests where it's our specialty for 2D hole arrays, because people want to pack more fibers in order to increase the bandwidth and increase the speed. So these are the type of products we produce. Here we see an example, 16 by 16 array of holes. Diameter is compatible with single mode fibers, so 126 microns. As you can see here, bottom right, the holes are actually never cylindrical. Most of the time, the requirements from customers are for 2 or 3 stages holes, which means a stage for the fiber, then the core and the cladding. And in the final part here, it's 1 or 2 millimeters where you can insert the core, and it's where we can reach the highest precision. When I say precision, means that we can have a control on diameter and hole positioning, which is in the order of plus minus 1 micron, which can go down with optimization to half a micron. So we can control these two parameters at half micron precision. When I say optimization, means that this is not only process optimization, but it's also linked to metrology optimization, and actually the interlink between metrology and process control. Because you can optimize what you can measure, and measuring with some micron precision, you know that it's not easy. You see here, for example, that for measurement of the whole diameter, when we can calibrate optical measurements with mechanical pin gauges, we can reach really high accuracy, high precision, while for the positioning where we are still looking for a way to calibrate optical measurements. Why optical? Because when you're going into real volume production, you cannot go with mechanical probes. Well, their accuracy and precision are not where we would like to have them. But nonetheless, we can produce this type of hole arrays in materials like silica or Borofloat. Borofloat is mainly for silicon photonics due to the CTI match. Thicknesses are typically between 3 and 10 millimeters. Tolerance, as I said, we can go down with optimization to plus minus half a micron. The holes can be fully customized in terms of shape, but also in terms of orientation. They can also be tilted to reduce Fresnel losses. As I said, the shape can be tuned to the manufacturing process or assembly process of the customer. We can customize the number of holes, the layout, the pitch. we can introduce also fiducials and markers for assembly. So we can produce a fully customized element that can be used by the customer in their own assembly process. Then we can go to waveguides. So we have the possibility with our technology not only to microstructure the glass in 3 dimensions, but also to write waveguides in glass. And this is done by actually densifying the glass locally with a laser and increasing the refractive index. We can increase the refractive index by delta n of 10 to the minus 2, 10 to the minus 3, which is enough to write 3-dimensional waveguides in glass, single mode or multimode. It is important to understand these waveguides are 3-dimensional, are not simply 2-dimensional like with other technologies. So you can also imagine to have a fan-in or fan-out, as we were talking about earlier, in 3 dimensions. So you gain actually in the possibility of packing more waveguides in the same volume. We have optimized our fabrication recipes for infrared wavelengths, obviously 1550, 1310, 1 micron, but this is extendable also to visible region, and we see also some requests coming now to extend to that region in order to increase the bandwidth. The mode field diameter, if we just stick to the infrared, is in the order of 6 to 10 microns. Circularity is pretty nice, 95%. Propagation losses are in the order of 0.2, 0.3 dB per centimeter. They can be optimized down to 0.1 dB per centimeter. Coupling losses are in the order of 0.2 dB per facet. This is linked to the mechanical polishing of the facet, so it can also be improved. What we cannot do, we cannot actually, let's say, deviate the light on tight angles because due to the mild delta n, our bands have a minimum radius of curvature, which is in the order of 20 millimeters at 1310 for 1 dB per centimeter losses. If you're doing tighter bands, then you increase losses. So for turning the light at 90 degrees, we have other means. I will show you in a couple of minutes. And we can also bring these waveguides very close, down to 20, 30 microns with negligible crosstalk in order to pack a lot of channels in the same volume. We can extend to multi-mode waveguides, and we can also produce a lot of different, let's say, devices based on these waveguides, both size converters, fan-in, fan-out, splitters, combiners. I'll show a couple of examples. We can also add fiducials and markers. In terms of examples, here is an example of directional coupler, where we are able, with a pitch of actually exit input and output pitch of 250 micron, we were able to switch the signal from the upper branch to the lower branch after 2 millimeters of propagation. And we had insertion losses for 50-50 splitting in your 1.6 dBs. Everything can be, actually, these were only for demonstration purposes, everything can be optimized for the customer requirements. We can do, as I said, one thing which is very often required for actually fiber connections linked to quantum photonic computing is fan-in, fan-out structures. Here we could demonstrate, for example, fan-in, fan-out structures going from 250 micron pitch at the entrance down to 30 microns pitch at the exit, or vice versa, with different layouts in terms of matrices. Channel counts were going up to several hundreds of these waveguides, and insertion losses in better than 1.5 dBs. We have also demonstrated similar multimode interferometer structures. Here you see an example, 1 to 5 dimensions. The physical dimensions were down to a few hundreds of microns, and we could have a peak-to-peak distance at the exit channels in the order of 10 microns. So that's for the beam routing. Then, as you know, when you are connecting fibers to chips, you also need some beam shaping. This can be done with micro-optics. We can produce microlenses, micromirrors, and arrays. Shape is totally freeform, or spheric or aspheric. Our technology is totally freeform in, let's say, by definition, so we are not limited to some specific symmetric shapes. Dimensions of the lenses can be fabricated, can go in terms of diameters from 10 microns up to 1 millimeter. Sags are in the order of few microns up to 100 microns. Surface quality, we have several recipes in order to polish these lenses, but we can go down to typically 10, 20 nanometers, or with the best polishing we can offer down to 5 nanometers for a shape accuracy, which is between 1 micron and 0.2, 0.3 microns, depending on the relationship between the shape, dimensions, sag, and diameter. Here you see an example. This was a lens array with a diameter of more or less 1 millimeter, ROP 3 millimeters, sag 40 microns, so pretty shallow micro lenses. We could reach surface roughness in order of 10 nanometers and a shape accuracy in order of 0.3 microns. You see here a bit more details on the lens we could produce. We can also bring the lenses very close to each other. We are not limited in the distance, lens-to-lens distance, like in some other technologies. At the beginning, I was saying that these three type of products can be produced standalone, but they can also be combined. The beauty of our technology is that you can combine these three elements, so micromechanical alignment with beam routing and beam shaping, so microlenses, waveguides, and Hall arrays in a single process step on a single machine. So not single process step, but on a single machine through several process steps. So you don't have registration problems. We can bring these elements on the same component with a precision in positioning the different element, relative precision, which is in the order of plus minus 1 micron. And this allows us to offer components with more than one functionality. So up to 3, 4, 5 different optical functionalities on a single glass component. So you reduce the cost per functionality. This allows very precise fiber-to-chip or chip-to-chip connectivity. It's cost-effective because it can scale up, and this can be scaled up in terms of, let's say, components, and so cost per unit, and also in terms of assembly and packaging. And here you see a sketch. Unfortunately, I cannot show you real pictures because these are covered by NDAs with our customers. But typical elements that we produce in terms of microconnectors, or monolithic, as we call them, microconnectors, contain, for example, Hall arrays to host the fibers, then a waveguide to keep the light contained, and while it's propagating towards, for example, a micromirror. It can be, as you see here, a flat micromirror, but it can also be an aspheric micromirror or parabolic micromirror that has two functionalities, actually, to redirect the light and also shaping the light. Then you can have even micro optics at the exit. And we have demonstrated, for example, similar microconnectors with at the exit, at the output, a spot size in the order of 20, 30 microns with a variation of plus minus a couple of microns. And an angle variation, which is also important if you're, for example, going for grating couplers, which is between 0.4 and 0.2 degrees. And here you see just some measurements on one of these components we have made, where the micromirror was a parabolic micromirrors, which is pretty difficult because then it's difficult to define it because you have two different axes. We could reach an average roughness in the order of 10 nanometers and a pretty good shape accuracy on both axes of the parabolic mirror. And with this, I'm done and I'm ready to answer your questions. Thank you.
Thank you, Rolando. Very nice presentation as always. Let me start with asking you how we could support your developments.
We have several axes of development where we work with partners, and we like also to get inputs. I would say fiber assembly, it's something we do not do, but our customers always more and more often actually ask for full solutions. We have one or two preferred partners we work already with since a few years, but we're always open to establish new partnerships, either in Europe or in the US or even in Asia. Coatings, it's also a very important topic. We are required, obviously, to supply components with high reflective coatings or metallic coatings. Metrology, as you have seen with the Hall arrays, to have reliable and fast metrological instrumentation is not easy, especially if you want to do it optically and possibly online or offline, but in a production environment. These I would say, are the three main topics.